It's very important that you form groups immediately. You know, if you're not already in a group, that you do that really quickly. We want all the groups to be 4, except where this is impossible. Then we, you know, if it's not possible, then we'll accept groups of 3. And under very exceptional circumstances, like everybody was in groups of 4 and there was only one person left, then we'll accept groups of 5. But groups of 4, maybe 3 are what we're looking for. So today we're going to be talking about words, and specifically about what is called morphology and how you model morphology using finite state techniques. Who here has had a linguistics class before? Okay, quite a few of you. Who can tell me what morphology is? What is morphology?
It's like the study of the forms of words.
The study of the forms of words, specifically the internal structure of words. Now, this is actually a common complaint we get. People will come into this class from computer science backgrounds and they'll say, linguistics? Why are you talking to me about linguistics? I'm a computer scientist. I don't need your linguistics. But the fact is that NLP is not just P. It's also NL. And the NL part comes from linguistics. And just as you would need to know something about biology to do computational biology, you need to know something about natural language in order to do NLP and do it right. If you were, in fact, linguists, we wouldn't have to talk to you about this stuff because you would already know it. So what is morphology? Well, the central idea is that words are not atoms. They have internal structure. And they're composed of smaller units that we call morphemes. And a morpheme is basically a minimal, meaningful unit. It's easy to forget this if you're working with English or Chinese, because a lot of English or Chinese words just have one morpheme. And they're not very morphologically complex languages. But even in English and Chinese, then there are morphologically complex words. For example, in English we have words like misunderstandings, where mis is a morpheme, understand is at least one morpheme, ing is a morpheme, and this s here at the end, the plural s, is also a morpheme. Each of these has independent meaning and can occur in lots of different words. So likewise, in Chinese, there's this suffix man that occurs mostly in pronouns, but can also occur with some nouns, like 同志, which means comrade. So you can pluralize comrade and say 同志们. So 同志, historically, I should say, meant comrade. Now it means something a little bit different. Don't laugh, you're bad people. So morphemes come in different types. They can be roots, or they can be affixes. And roots are sort of the center of a word. It's the part that carries most of the meaning of a word. And then there are affixes that change that meaning or add contextual information associated with that root. And affixes come in different types. There are prefixes, like in pre and prenuptial, or ir and irregular. Suffixes, like eyes in determinize, or in iterator. There are infixes, like fucking in Pennsylvania, or California, that come in the middle of a word. And there are circumfixes that come on either side. Like, who here studied German? Yeah, so to form the past participle of or a past form, a particular past form of German verbs, then you put g on one side and t on the other side, so you get things like gesammelt, for has gathered. So there are different kinds of affixes, but there's also what's called non-concatenative morphology. And this is where you change, rather than adding something at the beginning or at the end, then you make some kind of change. So there's umlaut, like in English, foot, feet, tooth, teeth. There's ablaut, which happens in English verbs, like sing, sang, and sung. There's root and pattern morphology, which is like umlaut and ablaut gone crazy. Has anybody here studied Hebrew or Arabic? Yeah, so these languages, it's like the root consists of like 2 or 3 or 4 consonants, and then you make new words based on that root by shoving vowels in between those consonants and like lengthening them or changing their quality. And this is called root and pattern morphology, and it's common in Semitic languages and other Afroasiatic languages. And finally, there's infixation, which we've already talked about. You might think from the English example that infixation is all about fun. It's not. Infixation is all about work. So in a lot of languages, this is very important to the grammars of languages, like in Tagalog, the national language of the Philippines. You do all sorts of grammatical stuff with infixation. More important than that, though, probably are functional differences in morphology. So morphology can work in different ways. This is very important for NLP, actually. So one way that morphology can work is as inflectional morphology. And this just adds information to a word that's consistent with its context. So things like number and tense and aspect and case, these are all examples of inflectional morphology. They don't change the meaning of a word. They don't change what word you're talking about. They just change the form of that word so it's consistent with the context in which it occurs. Then there's derivational morphology, and this is morphology that changes the meaning or part of speech of a word. So if you change parse to parser or repulse to repulsive, then this is derivational morphology. Now, one of the reasons that this is important is if you're doing things like information retrieval, then you want to get rid of the inflectional morphology. You want to normalize it away because it makes words that are the same word look like different words. But you don't want to do this to derivational morphology because it makes words differ in meaning and part of speech. I'm going to skip a few slides because we've got a lot to talk about today. And I added some new slides, so I want to get to those and have time for them. So morphology is largely a solved problem in NLP. Although people are still working on it, there are good solutions to morphology. And one of these is a rule-based solution based on finite state methods. It's been very well worked out, and that is often applied still to lower resource languages. There are also unsupervised methods in morphology where you don't need any labeled training data and you don't need to write a grammar or a set of rules. There are also supervised sequence-to-sequence models that are increasingly used that require training data. You have to label a bunch of data, but you don't have to write a bunch of rules, and so there's this trade-off. And for higher resource languages, then these are often appealing. When you're doing morphology, Yes.
What do you mean by like a resource language?
I mean, how many computational resources or NLP resources exist for a language? So for a English, we would say it's a very high resource language. There's a lot of labeled data. There are very good tools. Bengali, on the other hand, which is, I think, the 6th most widely spoken language in the world, is a very low resource language. There's very little in the way of annotated language data. There are some monolingual data, but you know, so that's what we're talking about. It's how much data there is and how many tools there are. Good question. Yes.
So do we use supervised for resource language or resourceless?
Usually for high resource languages, we would use more supervised techniques because there's more money to produce labeled data that you can use to supervise this kind of machine learning for high resource languages, and it's simply not available for low resource languages. But if you have a good grammar of a low resource language, you can write a morphological analyzer using rules that works pretty well without paying somebody to annotate 1 million training examples. So the basic problem here is getting, in morphological analysis and morphological generation, is getting between this form, which we'll call a lexical form, which is basically the lemma, the dictionary form of the word, and some set of morphological properties, usually inflectional properties. So getting between that representation of a word and the orthographic or surface representation of the word. And orthographic just means with reference to writing, the right way to write. So we're going back and forth between hug plus V plus prog and hugging. And in order to do this, it's often helpful to have an intermediate level of representation we'll call the morphemic form, where all of the morphemes are there, but they're in an invariant form. So every time that this S, for example, occurs, this plural S, or it also occurs in verbs, every time it occurs, then it has the same form. It's just an S. Even whether it would occur as ES or just as S in the surface form. So you factored out all of the differences between the realizations of morphemes in the orthographic form, and you put little carets or other symbols to divide each of the morphemes from one another, and added an end of word symbol that tells you when the word is over. So this helps you get from here to here. It also helps you get from here to here. So finite state transducers are a nice thing, and that's what we're going to be talking about today as soon as we get to them. Basically, they define regular relations between strings, like relations between our surface form and our lexical form. And these are widely used in practice, not just for morphological analysis and generation, but also in speech, especially a flavor of FSTs called weighted finite state transducers. And to understand them, then we first need to understand their simpler relative, the finite state automaton or finite state machine. And these should be familiar to a lot of you from theoretical computer science. Who here has encountered finite state automata before? So I think a majority of you. So finite state automata are nice. They're beautiful computational formalism. And when applied to morphology, they can tell you whether a word is morphologically well formed, that is, whether it's a good word or bad word, but they can't do analysis and generation. For that, we need finite state transducers. So let's get to finite state automata, sometimes also called finite state acceptors. They have the following parts. They have Q, which is a finite set of states, one of which, Q sub 0, is a special start state, and some of which, F, are a set of final states. We usually indicate the final states by drawing them double. Then we have sigma, a finite alphabet, and we have transitions between states. We have some transition function where we have transitions between states that have labels. And these labels are symbols drawn from sigma. So basically what the finite state automaton does is it encodes a set of strings that can be recognized if you can get those strings by following a path from Q0 to some state in F. Very simple. So let's see what a finite state automaton looks like. This is a finite state automaton for the famous sheep language. Now, I don't know what sheep say in your language, but in my language, sheep say ba. They do not say ba. They do not say bo. They say ba. And we want a finite state automaton that will recognize just valid utterances in sheep language. You know, it could be a long ba, ba. It could be a short ba. It can't be too short, though. We want to recognize all of those. And so we have this FSA. So who can tell me some strings that would be accepted by this FSA? What is the shortest string that it will accept?
B with 3A.
Okay, is that the shortest one it will accept? It will accept B with 3 A's followed by exclamation point. But that's not the shortest string it will accept. Yes? B with 2 A's followed by an exclamation point. So we would go B, A, exclamation point. Done. For B with 3 A's, then it's simply B, A, exclamation point. What about B with 1 A, an exclamation point? No, why not? So we go B, A, oh, no exclamation point. You can't go anywhere. What about BAA? Why is BAA bad? Why can't we do BAA? Yes?
It ends up in like a rejecting state. You have to reach like the Q4 in order for it to be accepted.
Yeah, we have to be in an accepting state, a final state, in order for it to work. So that's all there is really to finite state automata. I mean, we can prove all sorts of interesting things about them, but that's what you need to understand about them in order to pass this class. So there's one thing, though, that's a little bit confusing. So often when we teach you about finite state machines, we trace our way from state to state. We consume the symbols from the input tape until we reach the finite state. This is not wrong, but it can sometimes lead you to the wrong idea. What we're actually asking is whether when we ask whether an FSM accepts a string is there a path through the network that starts at the initial state, consumes each symbol on the tape, and arrives at the final state. So think about it in terms of like depth first search. Don't think about it in terms of I'm executing this and this and this. Oh, I didn't make it, I have to backtrack or something like that. No, think about it in terms of depth first search, and you'll be much better off. Another thing we need to talk about briefly is the subject of formal languages. Formal language is just a set of strings. It's typically one that you can recognize or generate with an automaton. So this is kind of different from natural languages, right? But a lot of work in NLP and computational linguistics basically has involved treating natural languages like formal languages. And the set of languages that can be recognized by finite state automata are called regular languages. And conveniently, most natural language morphologies belong to the set of regular languages. So this means that we can model them using finite state automata and other finite state machines. So we call this class of languages regular languages, and that should probably ring a bell, because what have you been banging your heads on the desk or on your computer about for the last week, culminating in today? What have you been doing with, yes?
Regular expressions.
Regular expressions. And the regular expressions you've been using are actually not real regular expressions because they have back references which are not part of true regular expressions. But they're a fairly convenient and standard way to represent something equivalent to a finite state machine. So we can write an FSA basically, really write a regular expression too, because they're equivalent. For every FSA, there's a regular expression, and for every regular expression, there's an FSA. We could write one that does English derivational morphology. So there's a lot of shorthand in this diagram from your book, but basically the idea is that noun sub I is all of the nouns that belong to this particular class. And adj sub al is all of the al adjectives. And so on. And then Is/v is verbal Is. So the /v you can actually ignore. So what this will do, if you write this out and expand all of the shorthand, so they've done something I really hate, but it's useful for shorthand, and that is they've treated labels of transitions. They've allowed strings rather than individual symbols. That creates no end of headaches, but it's easier to look at. So basically what this FSA will do is it will allow you to know whether a word is a well-formed English word or not. Is it a well-formed English word in terms of its derivational morphology? It doesn't do inflection, that's easy to add. But is it a derivationally well-formed word? It can tell you yes or no. Well, we probably want to do more than that, right? When we were back here, we wanted to go back and forth between lexical form and orthographic form. That is, we wanted to do analysis going up and generation going down. And a finite state automaton can't do that for us, but a finite state transducer can. So this is the basic problem. So we want to do parsing or analysis. We have a word as an input, and we want to output the word's stems or lemmas and the features expressed by other morphemes. So given geese, we want to return goose and plus n for noun and plus pl for plural. For gooses, which can't be a noun, this has to be a verb, meaning to pinch, right? He gooses me. Then it's plus goose is the lemma, it's called, the basic dictionary form of the word, plus v, plus third person, v for verb, third person, and singular. Dog can be either a noun, a singular noun, or a verb. Leaves can be either the plural of the noun leaf, or it can be the third person singular of leave. So we want, given these, we want to get these sets. So there are three solutions that we could adopt here. There are more than three, but these are three obvious solutions. So we could have a lookup table of some kind. We could have a trie, or we could use a finite state transducer. What would the advantage of using a lookup table be? Yes?
Relatively constant.
Constant what?
Lookups.
Lookup. Time. Yeah, it's be quite fast. What else? Yes?
Well, as long as your table's correct, it's always going to be correct.
Yeah, it's just based on whether the things in the table are correct. You always get that result. It's easy to debug. What else? Yes?
Yeah, it's simple to implement, just probably do a dictionary in Python or something.
Yeah, you might want something better than a dictionary, a Python dictionary, but you could start there. Yeah. So what are the disadvantages? Yeah.
Size is going to be huge.
It's going to be quite large. Yeah. Yeah. Yes.
It'll take a long time to set up because you have to go through every single possible word.
Yeah. So it's going to have a lot of redundancy in it too, isn't it? So you have to just individually go through for every word and provide the output. What else? Yeah.
Cannot handle new words.
Just think you can't do anything with a new word. You come across a new word, what do? It's not in the lookup table. You know, you throw up your hands in defeat. So what about a trie? Some people use tries for things like this. What advantage would a trie have? Yeah. So yeah, it depends on the design of the trie, but there are ways of doing the trie where it's more space efficient than the default table implementation. Like if you did a naive table implementation, the trie implementation could be made more space efficient. But what disadvantages does it have? Yes?
It's just like with the table, you still can't have new words.
Yeah, you have no way of dealing with new words. A finite state transducer has the advantage that you can write a finite state transducer that will deal with new words, that will guess lemmas, for example, when no lemma is given. And you'll learn a lot about this on your next homework, so stay tuned. You should listen very closely, actually, to the next part of the lecture, because it will help you with the next homework. So a finite state transducer looks a lot like a finite state automaton. There are a finite set of states Q, a special start state Q0, a set of final states F. But rather than having one alphabet, there are two alphabets. There are sigma and delta. And then there are transitions. There's a transition function between states, with each transition having a label consisting of two symbols. We conventionally separate these with a colon. So S here is the input symbol and T is the output symbol. So this works rather like a finite state automaton, except instead of having one input tape that you're reading from, you have an input tape and an output tape. And every time you go across a transition, you read a symbol from the input tape and you write the relevant symbol to the output tape. Now, one caveat. These can be more than just symbols. There's one other thing that you can have in a label other than a symbol for one of the alphabets. And that is epsilon. What is epsilon? Yes. The empty string. Epsilon is the empty string. So you can use epsilon to insert things and delete things, basically, because you can have a transition that has an epsilon on one side, or even both sides. So let's say we're tired of just talking to sheep, and we want to translate from sheep to cow. And if a sheep in my language says ba, a cow says moo. Or in this case, moo, because this is a cow who has lots of questions. So here is a finite state transducer that will translate from sheep to cow language. So if we give it, again, the shortest string that this will accept, which is the same as the shortest string that the sheep language FSA would accept. Then we start here at Q0. We go B, read B from the input tape, write M to the output tape. Read A from the input tape, write O to the output tape. Read A from the input tape, write O to the output tape. Then read exclamation point from the input tape and write question mark to the output tape, and then we're done. So we've successfully transduced ba to moo. And this will work for any string that's part of the sheep language. It will convert it to equivalent string in the cow language, because we have this loop here that means that we can handle an infinite number of different inputs. Any questions about this? Yes?
Is it always one-to-one character?
No. Or one-to-one character?
Yeah.
In a well-formed FST, it should be one symbol on each side of for each transition on each side of the label. So it should be either one of those symbols or the empty string. So sometimes in shorthand, people will write FSTs where they use whole strings on either side, and your book does that. But that's not actually how it works in real life. You just use single symbol or epsilon. But this doesn't mean that the strings are going to be of the same length, of course, because of the epsilon fact. And we'll get to another illustration of that in a minute. So the reason we would want something like this is illustrated most strikingly by languages like Turkish. Anybody here study Turkish? Yeah. You know Turkish? Okay. Don't criticize my pronunciation. Okay. Yeah. So Turkish is a language that allows a lot of suffixes. It's very rich morphology. And people make up new words all the time that have lots of different derivational morphemes. And so you can say things like "Uygarlaştır ama diklarımızdan misiniz kasına," meaning behaving as if you are among those whom we were not able to civilize. You can do this in Turkish. There are a lot of words. You couldn't list them all in a table. You'd have to have a way of dealing with the generalizations that are relevant to Turkish morphology. And you can do this with finite state technology. In fact, the very person who came up with this example wrote a well-known Turkish morphology using finite state techniques. His name is Kamal Oflazer, and he's at CMU Qatar. So here's the idea. So with an FSA, you could do things like this. You could write an FSA for English inflection of nouns. And basically, this is shorthand. Regular noun here means a transition for each of the regular noun forms. And then plural S means a transition just for the S that occurs at the ends of these, if they're plural. And irregular plural noun is a transition for all of the plural nouns that are not regular, that don't take the S. An irregular singular noun is a transition for all of those other nouns. And basically, you can add here a guesser. You can add a network that will let any other string be a regular noun. And then you can have a finite state automaton that will recognize any of the nouns in English, basically. Well, that's not very interesting because we don't want to just recognize nouns. We want to be able to generate them and parse them. So we can convert this to a finite state transducer that does that. So here for regular noun, we have all the regular nouns here, and then we, if we're doing parsing, we read epsilon, and we write plus n, and then if the next thing is a word boundary, then we write SG. We read word boundary, write SG, and that would get us to the final state. We could also read caret S, where caret is a morpheme boundary. It's a delimiter between morphemes. And then S is the suffix. And then pound sign here is the word boundary symbol. So we read that and we write plus plural. And so that, by that same logic, we can analyze any of the nouns of English that would be accepted by this automaton. Typically, when we're doing this, we want to separate concerns. We want to separate two aspects of morphology. One aspect is morphotactics, and this is basically how you put morphemes together, or maybe how you translate between the meanings of morphemes and their order. But for our purposes, how you put morphemes together. So an FST that maps between Zach plus N plus plural and Zach morpheme boundary S word boundary would be a morphotactic FST. It concatenates the basic forms of morphemes together. Lemmas with affixes. And these lemmas can be guessed, so they don't have to be stipulated. They can be made up, or they can be guessed by the FST. So that's morphotactics. But we also need to deal with allomorphic rules. These are rules that change the appearance of a morpheme. So for example, if we have Zach with the plural S, is this plural S? Yeah. Then we know that's going to be spelled Zach's with this E here. Even though that E is not always there with the plural S, it depends on the sounds and the letters that occur before it. So that's allomorphy, this kind of spelling rule, orthographic rule. And you're going to become very familiar with English orthographic rules. I'm just telling you right now when you do homework too. So keep that in mind. So here's an example of morphotactics, simplified. Here we're not dealing with properties like plus V, plus PL, anything like that. We're just mapping between the lemma and the inflected forms of the word, and not even all of the inflected forms of the word. So if we have this FST here, and we feed it the word walk, W-A-L-K. And we assume that the symbols on the left are the input symbols and the symbols on the right are the output symbols. Then what is our output from this FST? Yes?
I thought we would stay at Q0 because there's no empty string in left.
Empty string is everywhere. You know, there's an empty string here, empty string here, empty string here, empty string here, empty string here. Yes?
Could it be any one of like 3 things?
Yeah. In fact, this is an important aspect of FSTs, that they are not necessarily deterministic. So for a single input, you can have multiple outputs. In fact, you should view FSTs as returning sets rather than strings. So what is the set that this returns when you feed it walk? Yeah.
Walking, walks, and walked.
Yes, walking, walks, and walked. But specifically, what else is there in those strings? Is it just W-A-L-K-I-N-G? The caret. The caret, which is a, what is caret? Morpheme boundary. Yeah. Yes.